It's probably probable. This is problem 1162, as far from land as possible. Given an n by n grid containing only values 0 and 1, where 0 represents water and 1 represents land, find a water cell such that its distance to the nearest land cell is maximized and return the distance. If no land or water exists in the grid, return -1. The distance used in this problem is the Manhattan distance, the distance between two cells, x0 and y0, and x1, y1 is x0 minus x1 plus y0 minus y1, which is, essentially how many steps would it take to get from one cell to another cell. That's the Manhattan distance, right? Like if you had a 3x3, let's look at this 3x3 system, for example, right? What am I doing? I just drew an L and I just took an L the way I drew that. Okay, right? We have 1, 0, 1. I'm drawing this example here. 0, 0, 0, and 1, 0, 1. Right, the Manhattan distance between this item and this item is 2, right? Because you have to go 1 to the right and 1 down. So you could think of it as being like the shortest distance in terms of how far you have to travel to get from one grid cell to another, right? If I wanted to look at the Manhattan distance between two cells like this, right? It's really just the sum of, well, how far horizontally do I have to go plus how far vertically do I have to go, right? I have to go 1 horizontally, 2 horizontally, 1 vertically, 2 vertically, 3 vertically, 4 vertically. So it has a Manhattan distance of 6, right? This has 1 horizontal, 1 vertical distance of 2. So that can give you an idea of how Manhattan distance works, right? You could think of it as this, like technically this is the formula, right? It's the difference in the horizontal position plus the difference in the vertical position. And that's identical to just saying, well, how many positions horizontally do you need to move plus how many positions vertically do you need to move? That's the Manhattan distance, right? Versus like a Pythagorean distance, right? Where you look at like this and you draw a triangle. We're not doing that here. We're just thinking about how many steps do you have to travel to get from one cell to another. That's the Manhattan distance. Okay, I think I've exhausted describing that point. So in this problem, right, the cell that has maximized distance, that's a 0, in terms of cells that are 1, is the center cell with a distance of 2. The problem itself, the description is kind of wordy, right? We're trying to find a water cell, which is a 0, right? So we're trying to find a 0 cell such that its distance to the nearest 1 cell is maximum. So that's basically saying find a cell that's farthest away from all other. Find a cell that's a 0 that's as far as possible away from all cells that are 1, right? So if you wanted to look at each of these, right, that's the same thing as saying find a cell with a 0 that has the maximum minimum distance to a cell that's a 1, right? So I look at a cell that's a 0, like this cell, and it has a distance of 1 away from both of these, right? I look at this one, it also has a distance 1 away to both of these. I look at this one, it has a distance of 1 away to both of these. This one has a distance of 1 away to both of these. But this center 0, right? This center 0 has a distance of 2 away from both of these, right? A distance 1 here plus 1 here, 2. Right? The distance to this one is 1 plus 1 is 2. The distance to this one is 1 plus 1 is 2. The distance to this one is 1 plus 1 is 2. So there's a cell, right? And maybe we should do this again and kind of clear language. So if I thought of it as looking at this other array, right? I would say, well, all the 1s have distance 0 to a 1, right? So we're not going to consider that. If we look at this 0, it has an island, a cell with the value 1 that's 1 away. Same with these ones, right? Versus this center one, the closest one is they're all equal distance, right? But they're all distance of 2, right? I have to travel up 1 and right to the right one, or up 1 to the right one, to the left one, to the left one, up 1, whatever the distance is 2, right? So this grid kind of gives me the information of the minimum. This is really the distance to the closest 1, right? That's what this grid is giving me here, right? This is giving me the distance to the closest one, right? The distance to the closest one from 1 is 0, right? Because you're literally at a 1 already. So the distance to 1 is nothing because you are a 1. The distance from this 0 to the closest one is 1, right? It's either this one or this one. The distance to 1 from this 0 is 1, but the distance from this 0 is 2. So we're trying to find a cell such that the distance to the nearest land cell is maximized, right? So these are the distance to the nearest land. I'll call this the nearest one, right? Just to ensure that the language is reflective. So this is the distance to the nearest one. You see here, okay, the distance to the nearest one is 2. If you look at this problem, so maybe this one's a little bit more interesting, right? Right, we have 1 and then zeros everywhere. If we made this corresponding grid, well, this has distance 0 to the cell. And now what I want you to do while I solve this problem this way is take a note of how I'm approaching the manual kind of walking through this problem, because that'll give us some intuition in terms of maybe how we should approach this problem in an efficient way to solve it. So we have a 0 here, right? This 0 is 1 away. This one is 1 away. This one is 2 away. 2 away. 2 away. This one is 3 away. 3 away. And finally, this one is 4 away, right? Because in order for this cell to get here, it has to travel up 1, 2, has to go 2 vertical and 2 horizontal. So then the maximum distance for the nearest one is found at this grid cell here with value 4. Okay. So one way you could solve this problem, right, is you could look at all the ones in the system and find their distance to all of the zeros. Right, if I was to look at a 1, and I could say, okay, well, there's actually 2 ways you can think of this. Well, sorry. You could first look at all the zeros, right? You could look at each 0 and say, okay, what's your distance to all 1s? So you could look at this one and say, okay, I found a 1, so your distance is 1. And I could look at this 0 and play the same game and say, okay, there's a distance of 1. And I could look at this 0 and propagate like this and then find that, that was looking eerily like a symbol that we do not like. Oops, sorry about that. Right, so I could do that for each 0, right? So I could look at each 0 and then run some sort of traversal algorithm to say, I'm looking at this 0, look at everything around it, and try to find the nearest 1. And as soon as I find a 1, I terminate, and I use that value to save information. What I could also do is I could just look at each 1, right? The way that we solve this problem here, right, is that we started here, right? And then look at a 1, and then I could say, well, everything that's a neighbor to me is a 1 distance from me, right? So this is a 1 distance from me, and this is a 1 distance from me. And then I could look at everything that's a neighbor of that, right? And I could say, okay, let's highlight these 2. And I say, okay, well, everything that's a neighbor of this red thing, if this red thing has distance 1 to the land, that has distance 2 to the land, right? So all the neighbors of you have distance 2 to the land. For some reason, I keep forgetting to do simple things. And then from the green thing, I'd say, okay, anything that is 1 away from me, since I have distance 2, is distance 3 from the land. And anything that's a 1 away from me, and I'm yellow, and I have distance 3, is distance 4 from the land. Has distance 4 from the land. So this looks eerily like breadth first search, right? The idea of breadth first search is you start at a cell and then you explore all neighbors. And then you explore all your neighbors' neighbors. And then you explore your neighbors' neighbors' neighbors. And you propagate that way. Right? So for this problem, it's pretty simple to see because there's one island. So I could literally just look at an island and I could say, well, I'll traverse all my neighbors and I'll find all their distances to me. Right? And all my neighbors' distances to me. And since I'm the only island, that will be the distance. That'll be the minimum distance to an island from that water cell, right? That'll be the minimum distance for any 0 reaching a 1, right? Running it like this. And how would that work in this problem? Well, what you could do, right, is you could start here, right? And you could run the algorithm through like that, update the information, right? And then you could start here and run the algorithm through, store that information, and just keep doing that for each one. But what we're looking for is the nearest island, okay? So one way you can think of this is like an expanding system, right? So what if instead of using one, like looking at one and then looking at all the neighbors to see the closest one to that island, saving that information, looking at another one, looking at all the neighbors to find the closest island, saving that information, looking at this one and doing that for each one. What if instead we thought of this problem like this? We could say, well, we're just trying to find the distance to the closest island, right? So if we just kept like a system of all the islands' positions, right? We're just trying to find the closest one. So when we explore this information like this, we could build our system like so, right? So everything is 0 here. Because I guess the idea is we're just trying to find the distance to the nearest island, right? So if we had a system of all the islands, we could run breadth first search from here, and then we could get a distance 1 away from all the islands, a distance 2 away from all the islands, and as soon as you traverse water, you would know that's the minimum distance to get to that island. It's so difficult to explain this point. Okay, so if I ran breadth first search here, the neighbors would be what? It would be here, 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 and here, right? Because these things have this neighbor, this neighbor, this neighbor, this neighbor. So then all of these would have value 1, 1, 1, 1. Ugh. And then what's the neighbors of these cells that we haven't explored yet? Well, it'd be here, 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 and here, which would mean that these have value 2 away from the system. So I guess the idea is, if I had to summarize it and articulate it in a way that makes sense, I'm trying to find what? I'm trying to find the distance to the nearest one. So if I run breadth first search on the systems of ones, every iteration will get me an additional distance from those system of ones, right? So you can imagine it's like all these system of ones and it's like reaching in. So there's these system of ones, and after each iteration, I'll get distance, additional distance of 1 from those ones, right? So I get the system of ones. I find everything that's a distance 1 away from the islands. Man, this makes no sense what I'm saying, right? Let me try to write down what I'm saying. Maybe, hopefully that'll be a little helpful, because it's not, I'm not articulating it properly. Right? So what we're trying to find is the distance to the nearest one. I'm writing down the same thing. For a 0. Right? So I'm trying to find the distance to the nearest one for any 0. Okay? The distance for each 1 to 1 is 0. what I'm basically saying here, right, is like for all the ones, the distance to 1 is 0. The distance for each of the neighbors of each one is 1. Is at most 1, I guess. What I'm basically saying is, for any of the neighbor of an island, the maximum distance to an island is 1, right? Because for any island, all the surrounding cells will have a distance 1 to that island, right? If I have a 1 here, and 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 a... what the hell am I drawing here? Right? One thing that's definitely true, if we think of this, right? For all of these cells, right? The distance to 1 is 0 for everything here. And then for all of the cell's neighbors, right? Their distance to a 1 is at most 1, right? It can be at most 1 because it's 1 away from a 1. So I can just say, okay, everything here, the distance is 1. Everything here, distance of 1. Everything... sorry, that's not right because I can't go vertically. Everything here, distance of 1. Everything here, distance of 1. Everything here, a distance of 1. Right? For all my neighbors that I can travel in one step, it has a maximum distance of 1. Right? And then for all of those neighbors, right? So for all the ones, neighbors, they have a max distance of 2. So hopefully this makes it a little bit more transparent what I'm trying to do here. But to be honest, it is kind of hard to do all this. Right, so that's where the breadth first search idea comes into play. Right, so if I explore a 0 and it hasn't been explored yet, that means that's the minimum distance to get to a nearest neighbor. Right, so I'm basically looking at all the ones and I'm running BFS to propagate through the system to find the nearest one. And if I haven't explored a node yet, and since we're using BFS, we're going level by level, right? I look at everything of distance 0 before I look at everything of distance 1, right? I looked at all the blue nodes before I looked at the red nodes. I looked at all the red nodes before I looked at the green nodes. So as soon as I traverse a node, that means I found the minimum distance to get to one of the islands, right? So essentially this problem becomes the closest neighbor of an island is all of its neighbors, right? For all the islands. The second closest neighbor would be all the neighbors of all the islands. The third closest neighbor would be all the neighbors of the islands, right? And I would just keep propagating the system like this, and you'll notice that this looks exactly like breadth first search. So that's what we'll essentially do to solve this problem. I apologize if that didn't make a lot of sense. I was really trying to articulate my points. I think the last graphic was probably the most helpful. So let's go ahead and get right into this. So we'll create a scene array to say that we've already seen something, right? Because if we've already traversed a node, that means that since breadth first search is always increasing in distance, right? We start with distance 0, then we look at distance 1, then we look at distance 2, and then we look at distance 3. If we're looking at something that's already been traversed, that means it was traversed with a lower distance, right? So like in this example, let's try to contrive an example where that makes sense. Right, so if this was the system, right? So we would traverse these two with distance 1, then these two with distance 0, and then traverse these two with distance 1. And then you may feel like, okay, when this system gets traversed, it'll look here. But this 0 has already been traversed with a lower distance, right? Because breadth first search is always propagating outwards and increasing distance. So since this green 0 has already been traversed, any subsequent traversal will have a higher distance. So that would mean it corresponds to a higher distance neighbor. So we don't want to consider it. So we'll create this scene array to articulate and just catch or save whether or not we've already traversed a cell already. Already. If we've already looked at a cell. Times length of grid. For blank in range length of grid. Okay. And then what we want to do first, right, is the way that we propagate the system, right, is since we start with looking at all the ones, we want to somehow look at all of the ones first, like this, add them to our system, right, and then add all of their neighbors to the system. Red is next, I guess. Right, so you add all the red ones to the system. And then so on and so forth. So you don't want to, I guess what you don't want to do, and each time you want to gauge that you've seen both of these, all these values, right? So you've seen this, so you just mark that information, I guess. So what we'll do is we want to add that to our queue. So when you run breadth first search, right, you create a queue. And we'll say queue equals nothing. And then we'll look at each item in the grid. So for I in range, length of grid. For J in range. Remember, it's an n by n, so I don't have to do length of grid 0. Okay. So if the grid at ij equals 1, right, this means it's an island we want to traverse the distance from. We'll say q append ij. What is that ij pairs to represent the nodes, the vertices? Okay, and then we'll say while q. I guess we should also say that this has been seen. So we'll say seen of ij equals 1. Representing that we've already traversed this node, right? We don't want to traverse the 1 again. Right, this will greatly impact our runtime. So while q, what do we do in while q? While q. So we'll look at each neighbor, or for each member in the queue. So how's this gonna work? So we should probably make something that is the distance. We'll set it equal to -1, just in case there is no solution, right? Because if there's no solution, right, we should return -1. We'll call it min distance, I guess. And then current distance, that's the distance of the solution so far. So we'll create a new queue that will update. We'll look at each element inside of the queue. We'll look at each neighbor. So how many neighbors are there for each element? Well, you can go left, you can go up, you can go right, or you can go down. Right, so I'll look at each neighbor. So I have I minus 1, j. That'd be my up neighbor, my top neighbor, I guess. I have I plus 1, j, my bottom neighbor. I have my left neighbor, which is I, j minus 1. And then I have my right neighbor, which is I, j plus 1. So I'm just saying, for all my neighbors, if they're valid neighbors, what does that mean? Well, if 0 is less than or equal to k, which is less than or equal to, or less than the length of grid. So I'm just doing this to ensure that they're in boundary. And so I'm just ensuring that that my neighbors, I'm not like choosing a negative neighbor or a neighbor that's outside of the range of the grid, right? Because it's a fixed box grid, but you might end up like trying to look at items that are outside of the constraints of the size of the grid. So this just ensures that you're in the grid and you haven't seen it. So that would mean that seen of KL equals 0. So I'll just say and not seen. I think that's descriptive enough. So it's not been seen. Well, that means that the min distance for this item, right, is the current distance plus 1. So I'm basically saying whatever the current distance is, right? If I haven't seen this item yet, right? If I haven't seen this grid cell yet, that means that there has been no island that's closer to this grid cell. And this grid cell's a 0. So this grid cell's a 0, so I can traverse it. And it hasn't been seen yet. So whatever the current distance is of breadth first search, whatever how far I've gone so far, that's the nearest neighbor for this system. And this is always increasing. So that means that the min distance to a neighbor is just increasing, right? Remember when we ran this problem here, it was increasing and increasing and increasing. So if you were looking at this last cell here, right? And it's continuing to increase. If you haven't traversed this yet, this will be the maximum distance, which is here, which is 4. Okay. And then you want to add this to new queue. So this is a new neighbor we're going to traverse. I always forget we're adding this to prepare. And then when you're done, you just set queue to the new queue that we created. And we increase the current distance plus equal 1. And at the end, you just return the minimum distance that you found. Scene is not defined. I just called it S for some reason. Let's just call it scene, whatever. This is already a super ugly solution, but not really feeling it today, so it is what it is. Okay, that doesn't sound good, that it's scrolling forever. There's probably some sort of infinite loop here that I'm not seeing. Yeah. Oh, okay, sorry. So if it hasn't been seen yet, now that I've added it to the queue, it's officially seen. Right? As soon as I add it to the queue, that means that there's no reason to traverse it anymore, right? Because it's a race. Whoever reaches this cell first, whichever one of my islands reaches this grid cell first, that's going to be the closest distance, right? This problem is basically like, which one of, let's imagine, I don't know why this came to me, but let's imagine you're on the playground and you're a kid, right? And you're going to say, which one of my friends am I the closest to? Meaning like in terms of distance. I'm on the playground, there's people all around me. I'm the 0 cell and they're all the 1 cells. If all of them ran the same speed and they all took a step towards me every second, an equal step towards me, whoever reaches me first is the person that I was closest to. Does that make sense? That's essentially what we're doing in this problem, right? You can imagine that you're on a playground and there's all these people around you. The person that's closest to you is the person that can reach you first if they all move towards you at the same time, at the same speed. Right? Everybody takes a step. So all these islands are like encroaching, I guess. They're all moving towards things that they're close to. And if they reach a grid cell first, that means that's the closest island to them. And that distance is the closest distance to the distance to the closest island. Okay. I wish I said that earlier because there's probably a lot of people who were watching this and were like, this doesn't make any sense. This guy's just rambling. But that's the basic idea of this problem, right? So if someone reaches me, that means that I've been seen, right? I don't need to consider anybody else that can reach me because whoever reaches me first, that's the closest distance. So I don't need to explore this node anymore. So I'll just set this to 1 to say, okay, I don't need to consider this node in the future. All right, let's go ahead and submit that. All right, cool. So what's the runtime and what's the space complexity? Run complexity, space complexity. So let's say that n is the length of grid. So let's just say that n is the length of grid times the length of grid. Yeah, whatever. Let's just say n is the length of grid, whatever. So there's n times n elements, right? Because it's an n by n. So there are n times n elements. Okay. Now, we have to create this scene array to measure everything that we've seen so far. So it's definitely going to be, let's do space first, right? There's definitely going to be n times n grid cells that we have to save information for, right? And the queue never gets bigger than n times n, right? Because maybe all of the cells are ones, so you end up adding all of the grid cells to the queue. So that's another n by n squared elements that you have to have space for. But, you know, it's never going to grow bigger than seen, right? Because you're never going to add more elements than the total elements. And since you only look at each element once, it'll never get added to the queue more than once. So they're at most big O of n squared. Right, now don't get concerned with the fact that this is n squared, right? Because n squared is the number of elements. So it's still linear in terms of the total number of elements in the system. Okay. And then in terms of time, well, we have to create this array. That's going to take n squared time. We have to look at each element to figure out if there's ones that we need to add to the queue. That's going to take n squared time. We look at the queue, and we look at each element in the queue. And we look at all four neighbors. So the queue and the queue and the queue, what? So the thing is, and it may not be super intuitive, but since I'm saying seen of KL equals 1, I only look at each cell at most once, right? I look at all the cells in the queue, and I add all the neighbors. But each cell will only get explored once because I only add it to the queue once. Because as soon as I add it to the queue, I note that I've added it to the queue. That way, in the future, I never add it to the queue again, right? I only add something to the queue if it hasn't been added to the queue before, right? Because every time I add something to the queue, I note that, right? I add something to the queue, I note that. So I never add it to the queue twice. So every cell only gets explored once. So I look at each cell in the queue one time in this whole process, and I only look at its four neighbors, right? So each cell, I look at all four neighbors. There's n squared cells. I look at the four neighbors. That's 4n squared. That's big O of n squared. And again, n squared is the number of elements, so that's linear with the total number of elements in the system. Okay, guys. Again, this is another day where the solution was just a bunch of rambling. Hopefully, I improve in the future. I don't know.